All right, well, good afternoon, everyone. Today we're going to start talking about what happens in mechanics after you get to the yield point, when you get to the yield point, and after you get to the yield point. And in order to introduce this topic, we're going to talk about and solve problems of Wellbore stability. Basically, in Wellbore stability, what you want to, your objective is that the cavity remains stable, so that you don't have failure of the rock around the wellbore, so it remains stable. And there are basically two types of failure around the wellbore that you could have. One is going to be shear failure, where most of the compression locates, but you can also have tension. So simultaneously in a wellbore, you can have tensile failure and shear failure. And that's what we're trying to determine. We're going to use the equations of elasticity and the Kirsch equation, something that you have already used when we were computing stress around the wellbore. But before we were assuming that everything is elastic. Now we'll continue assuming that everything is elastic, but we're going to look for those points that exceed the stress delimited by one of these shear failure criteria or tensile strength failure criterion. And that's what we're going to discuss today, the tensile failure and the shear failure. So as you can see in the first part of the project, you're going to have to determine what is the shear failure criterion for this rock. Here, these people that, I didn't put the reference, but somebody measured, I think I took it from Jagger's book. Somebody made measurements of what is the shear strength of this rock, and we're going to see what are the equations that we need in order to fit to that data a shear failure criterion. So with that, you will be able to say when there is shear failure around the wellbore, and also you need to know what is the tensile strength. So for that, we don't have measurements for this particular rock, but if you read the part of tensile strength in Jagger's book, you will see that based on shear strength, you can get an estimate of what is a reasonable tensile strength. And all of that, we're going to put it into wellbore stability. We have seen a little bit about hoop stresses and radial stresses when we were talking about stresses around a cavity or stresses around a fracture, but we didn't talk much about wellbore stability. And although the project is about wellbore stability, I expect that you do that reading on your own, okay? And I'm working on this chapter about wellbore stability, which is going to be uploaded very soon. And hopefully, you know, I'll try to finish it by Thursday. So that you can use that together with this project in order to solve the problem that you have to solve. It's going to involve, I think this is the most coding intensive project of all the projects, because you need to solve equations around a wellbore, but not only just a vertical wellbore. You're going to have to go read all of that, go towards the end of the chapter, and then, are you familiar, guys? You remember these matrices? And so you're going to have to compute the stresses. Let me zoom in here. Stresses in the, now it's going to be the coordinate system of the wellbore, because you're going to have a deviated wellbore. So we're going to do wellbore stability analysis for deviated wellbores. And in deviated wellbores, if you know what are the principal stresses, after that you compute the tensor in the geographical coordinate system, and after that you apply another transformation in order to get it into the Wellbore coordinate system. After you get stress in the Wellbore coordinate system, which are going to be these ones, you can apply these equations that are going to be the stresses around the wall of a deviated Wellbore. And when you have these stresses now, then you have to go one step further. You have to compute principal stresses. So calculate eigenvalues out of this, and out of these eigenvalues, you're going to be able to say if this is at failure or not. So, and after you do all of that, you're going to have to plot your solutions for all possible deviations of a Wellbore. So let me explain you what that is. So Wellbore stability then basically involves computing around the Wellbore when there is shear and when there is tensile strength, if any. And this is very well explained here. If you want, something I can do is I can upload the version I have right now, which is kind of like a rough version. I'm still working on it. You see, I didn't do all of those updates. But so you can get started. All the main equations, everything is already there. But I just wanted to flow smoother. So I'll do that for you guys. I'm going to upload this right away. And there you will see the equations that are needed in order to see if in a Wellbore there is tensile failure or shear failure. And look, I have a mini Wellbore here. This is a mini Wellbore, and whenever you have stresses, if you were to apply stresses only in this direction, let me zoom out a little bit, and actually this will be like this. We're applying a lot of stress in this direction and almost no stress in this one. Actually, we failed it in the lab, this one, just by applying stress in this direction. What you would expect to see is, let me put it over here, you would expect to see tensile failure in this direction at these points over here, aligned with the direction of the maximum stress, and you can see very clearly those tensile fractures right there and there. And on here on the sides, you see how it's red around that area? That's because your hoop stress is very high. All your stresses that are going into travel in this direction, they have to sort of bend and go around the Wellbore in order to make it to the other side. And when they do that, they localize in this region. At this point is where you have shear failure and you have breakouts. Look, do you see in there? Let me see if I find the right angle to see those breakouts. Probably you can see there a little bit, but wait, I'm going to play with the light. So yes, so I get those to show up even better. Okay. You see those marks? Okay, that is shear failure around the wall of the Wellbore. And let's see if I can do it from this direction. And not that good. All right, so there you can see it. Oh, there you see very well, okay? So all of that is shear failure, and that happens because you have a very large stress anisotropy in this region. The stress in this direction is much higher than the stress in that direction, and because of that, you have shear failure. And basically, this is what you have to do, but you have to go one step further and compute that for deviated Wellbores. In order to plot all possible solutions for a deviated Wellbore, you're going to use something which is called a stereo net plot or a lower hemisphere projection. So let me tell you what this is. When you analyze the stability of deviated Wellbores, you can do a general analysis in which you plot the conditions of stability for any wellbore at any arbitrary direction. In this lower hemisphere projection, imagine that here you have, this is half a sphere, right? And you're looking from the top. A vertical wellbore is a point that hits the lower hemisphere in the middle. A horizontal wellbore going to the east is it's a line that hits the lower hemisphere projection just at that point. And in general, at any arbitrary orientation, you can tell what is the deviation of the wellbore and what is the azimuth of the wellbore in which direction is going with respect to the north. Here in this case, that point, this is the north, and therefore here is the south, here is the east, and here is the west. And for example, if you had a wellbore going in direction northeast at a deviation, this is 0 deviation, this is 90 degrees deviation, at say a 30-degree deviation, it would be a point somewhere over here. Let me help explain that concept with an animation in case what I say wasn't super clear. Okay, so let me start this again. So here, don't pay attention to that line for now, because that line, it's about faults. But this lower hemisphere projection is this one that we have over here, right? Where the line from here to there, in our case, will be the orientation of the wellbore. And the point in which that wellbore, or that orientation, that line, hits the lower hemisphere, that is the point in which you plot a given quantity. For example, in our cases, if I switch to this solution, you are plotting in a polar coordinate here required unconfined compression strength. So you can do a surface map of where you need, in this case, the strongest rock in order to avoid shear failure. So let me ask you, just looking at this plot, what is the least convenient direction to drill a wellbore at this location for this case, based on what we just said? So usually red, red means bad, right? So it's this region. This plot is telling you that if you were to drill a wellbore, a horizontal wellbore, at about 20 degrees from the east towards the north, you will need a very strong rock with about 100 MPa of unconfined compression strength, and that's a large number, 100 MPa unconfined compression strength. Otherwise, you will have breakouts. You will have failure, shear failure. And on the contrary, the most a favorable direction to drill a wellbore will be this one, a horizontal wellbore, drill going in direction from the south 20 degrees to the east, horizontal, and in this location you will need a much, it's a lower UCS, still a decent unconfined compression strength. And the intermediate will be, in this case, a vertical wellbore. Notice that always the worst condition for drilling a deviated wellbore is a condition in which, perpendicular to the wellbore, that plane has the maximum stress anisotropy. And in this case, for example, this is a normal faulting case. Let's see, it's normal faulting. Yes, SV, SH max, SH min. So the largest stress anisotropy is in a plane that contains SV and SH min. And that's going to be this plane, perpendicular to SH max. Okay. So what, Rod?
Just talking. So
Okay.
just understanding what the charts are finally showing.
Yeah. So the chart is, you can plot many things here. You could plot unconfined compression strength. You could plot pressure of the mud. You can plot required tensile strength. You can plot many things. It depends which is the variable that you solve for.
Well, I mean, as far as like what the axes are, it's like actual wellbore orientation you would be drilling.
Every single point in here, it's a wellbore orientation. And I didn't say this, but so deviation 0 will be vertical wellbore is here. This deviation 30, 60, 90. 90 degrees horizontal wellbore. So depending, and this is why stresses, the state of stress is very important. The direction of the stresses and the difference, the relative difference between the stresses is important because that's going to tell you lots of things, like, for example, orientation of hydraulic fracture, orientation of faults, the ideal orientation or the most likely orientation of faults to be reactivated in shear, and also what is the best and the worst condition for drilling a wellbore in a deviated wellbore in a given location. Okay.
How do we obtain these plots?
You do Google and plot polar plots, polar surface plots, something like that, and then you'll find it, I'm sure. And you can do it with Python or with MATLAB. You will see.
How do you know they require the UCS
That's what we're going to see now. We're going to see the equations that we need. So, but up to here, you know, this is something you already know, and it's not going to be too difficult. First of all, it's just calculate the stresses around the wall of the wellbore, around the wall of the wellbore. That's basically finding these transformation matrices, very similar to what you did before for faults, but now you have to put this in the coordinate system of the wellbore. And then with Kirch's equations, which is something that I'm going to give you, right? These Kirch equations are over here. Those are the Kirch equations, and then out of that you compute the eigenvalues of that matrix, and you'll get something like this, where this is the worked out equation, right? But you could also compute eigenvalues instead of writing this equation again. And once you have the principal stresses at the wall of the wellbore, you're going to be able to apply the equations that we're going to discuss right now. Okay? So the homework just consists on computing stresses based on elasticity and comparing those stresses with a tensile or a shear failure criterion that we're going to talk about right now. Okay? All right. Okay. So that's the motivation for starting to talk about plasticity and inelasticity, and later we'll get into some other applications of plasticity theory and elastoplasticity. All right, so we start talking about plasticity and inelasticity. So far, we have been dealing with systems in which, when we said that we were doing linear elasticity, stress was proportional to strain. You could load a material, and you could unload a material, and it will follow the same path. All of these, if we have a linear relationship, then let's say we use Young modulus as the proportionality coefficient. If this one is constant, then we have linear elasticity. And we have linear elasticity, or in general, in all problems of elasticity, the strains are recoverable strains. So you go up to this point, you decide to come back, and you come back to the same line, you can recover the strains. There are no irrecoverable strains. We didn't talk much about this problem, but you may find this in some other applications. You could have systems which are elastic, but they are not linear. For example, you could have something like that, in which the more stress you apply, the stiffer the material gets. And in this case, also, you could load in this direction and get to this point, and if you want, you can load in this direction, and you will go through the same path. As long as the solid is elastic, you're going to have all recoverable strains. Examples of this case in which now you have a tangent Young modulus, it varies as a function of strain. Examples of that are, for example, granular media. In granular media, as you start to apply more stress, if you were to zoom in here at the contacts of the grains, you will see that the area of the contact, and if I plot it as a cross section, will be that, is proportional to the stress you apply. So the more stress you put on this, the larger this contact gets, and the more area you have the contact, the stiffer the material gets. That's a very well-known property of granular media. They are stress sensitive, and the more stress you put, the stiffer they get, as long as you remain within the elastic domain. And another example of these are also fractured rock masses that have fractures inside. As you apply stress on those, the fractures start to close, the walls of the fracture start to touch each other, and the material gets stiffer and stiffer as you apply more stress. Always, if you don't produce any kind of failure or any kind of inelastic strain. But the idea in these materials would be that they are elastic because the key is that all strains are recoverable. On the other hand, when we go to inelasticity, we go into materials that you can load them at a certain amount, but at some point you're going to get to something which is called the yield stress. And at that yield stress, the material can deform with no additional increment of stress. And if you were to unload this material, we can idealize it as going down with the same slope as it went up. You will have now a strain which is something called a plastic strain, or also a irrecoverable strain, because you unloaded it, but you do not come back to the same point. And that's why this is also called inelasticity, because it's not elastic anymore. In this case, we're going to see that there are several cases later on that can happen over here. The material sometimes gets stiffer, but not stiffer, but might get stronger after a yield point. Some other times maintains the same strength, and some other times it decreases, right? This one, for now, we're going to call it, this is an ideal plastic deformation, in which the yield stress, that value that we can call sigma y, and the y comes from yield stress, is the maximum stress that the material can support. You cannot put stress higher than that in the material. Usually the way, for example, I'm positive that you have seen this before in a material class. If you were to test the yield strength, for example, of steel, what you would do is you grab a rod of steel, then you put a force or a stress on that bar, and you pull until you get to a maximum value. That maximum value where there is no more linearity between stress and strain, that's what is called the yield stress. We're going to come back to this example of steel in a minute. Before we go into getting into equations, I'd like to see some examples of inelastic strains, because I think that sometimes, you know, inelastic strains are a little bit disregarded, especially in petroleum engineering, but they are everywhere. So you need to know when you need an inelastic model, or when you have to consider inelastic strains and when you don't have to consider those. But they're almost everywhere. All right, so let's talk about some examples. What is the first thing that you do when you're looking for oil and gas? I hear seismic. Okay, so do you think there are inelastic strains in seismic? Yes, no?
Unless you have a really strong hypersite now.
Yeah, right. Unless you get the T-Rex track. Even beyond that. Well, even if you had an earthquake, probably, then you will have for sure inelastic strains, right? Well, actually, talking about earthquakes, my example is very close to earthquakes. But if you do normal seismic, there's very, very little chance that you are going to have plastic strains. But usually when you are looking for places for oil, or you want to design for example, you may want to see whether the stresses in a given location. An example of inelasticity, more than inelastic strains, of inelasticity, is the determination of in situ stresses by assuming that the faults are at shear failure equilibrium. What that means is that we know that we have tectonic plates, right? And those tectonic plates, they are constantly moving and applying stresses on the Earth's crust, and they change the stresses. If you compress something, you will expect to have a higher stress in that direction, and but there is a limit for that. You cannot apply stresses forever, or tectonic strains forever. The stress is not going to go forever. At some point, you're going to break some of the Earth's crust, and when you break the Earth crust, you're going to produce faults. Okay, so this is a fault. This is a fault in which there were tectonic stresses either in compression regime, in this case is an extensional regime example, in which you create this continuity in the subsurface. But this is just shear failure. This is stress that have gone beyond an elastic limit. And after that elastic limit, you can compute the magnitude of stresses in the subsurface by assuming limit equilibrium. I know the guys from Geotech, they are familiar with this concept of limit equilibrium. So you can apply the same concept of this limit equilibrium, assume that the Earth crust is about to fail, or it is failing as we talk, and with that you can determine in situ stresses. Usually you may not expect to have these determination to be super accurate, right? But it can be a lower bound and upper bound for what you want to measure, and this is going to be mostly like this. The maximum principal stress is going to depend on the friction angle of the material that you are considering and the minimum principal stress. This is an equation we're going to see later on. But basically, for example, in this case, let me change actually this example here because I wanted to make a point with tectonic strain with horizontal stresses, but this is an example of the fault is moving like this, so it's a normal faulting example. In this case, this will be the minimum principal stress. According to this equation, the minimum principal stress depends on the effective vertical stress according to that relationship. This one cannot be any lower than this value divided by that one, because otherwise it will fail. It will be a failure. So in geotech, that's what you consider passive pressure.
Yeah, passive versus pressure.
Yeah, so it's passive versus active, right? This will be passive when your horizontal stress is lower than the vertical stress. Then it will be active when you have a lot of tectonic strain limiting what is the value of the maximum principal stress. But the idea is that faults are a failure and those control your stresses. So even before, when you're considering fault traps and state of stresses, if those faults are sealing or not, already inelasticity plays an important role there. Let's say that we found oil at this location, and actually I already draw what we're going to do next. So what do we do next? We're going to drill a wellbore, right? So when you drill a wellbore, inelastic strains and plasticity are going to come into the picture because first of all, you have to do perforations. You have really to cut the rock in order to do that hole. So all of that is going to be inelastic failure. And after that also we need to guarantee wellbore stability. And guarantee the wellbore stability, that's going to be prevent shear failure and prevent tensile failure in the wellbore. And this is actually our project. So within all those types of applications of inelasticity, the one that we're going to address is wellbore stability. But remember that there are many more.